So we're now going to be talking about inverse functions, which is the last video that will be talking about functions and properties of functions. We're still going to talk about functions throughout the rest of the semester here, but we'll actually be talking about specific types of functions and looking at the properties of specific types of functions. But here, inverse functions are what we're going to be talking about in this video. Now, inverse functions are extremely important. They're very useful. They're used in upper level math classes, and not just upper level math classes. The concept of inverse functions or inverses are widely used in engineering applications. Without going into this specific detail, there are things called Fourier transforms, and then there's also something called an inverse Fourier transform. It's the same concept of inverse functions. A little bit more complicated, but the same idea of inverses here. So what is an inverse function? Well, I'm going to draw a couple bubbles here to kind of have another way you can think of as having functions. So remember, when we were talking about a function, we had a set A and a set B. And so we had something in the set A, and we were using a box to represent this, and set A is my input, and then set B is my output. So this was x here, and then my output was f at x. And then, of course, my rule or equation was just f. And this kind of mapped here, and I'll go ahead and put an arrow to indicate we're going from the left to the right. So we're doing function, just evaluating a function here, sorry. And remember here that for a function, we called this set the domain, and then the range of f wasn't necessarily b, but it was sitting over here. This is the range of f. So domain of f, and then range. Now, inverse functions are basically going backwards. And so we would take this point here that we started with, and we want to go backwards now and get to what we originally had. So I want to get back here. And so the key thing here is this would be, we label this as f inverse here. So this actually becomes the domain of f inverse, and this becomes the range of f inverse. Now, f inverse is just denoted with f to a -1 there. Now the key thing that I like to think about, just the general concept of an inverse function, is an inverse function output undoes the original function. Okay, so it undoes the original function. Alright, well, what do we mean by that? Well, let's just look at an example here. If, for instance, we had f at x equaling x plus 2. The inverse function is actually something fairly easy for us to get without even having to have a definition down or anything. If we use this kind of generic undoes a function, well, what does the first function do? It adds 2 to every value x. Now you want to undo that. Well, if you add 2, undoing that would be, of course, just subtracting 2. So the inverse function here would be x minus 2. Now that's all well and good, but the problem is when we get into more complicated functions, or just more complicated problems in the end, we need to have a much better, more formal definition. One, so that we know if functions are inverses of each other, and number two, so we know how we can find inverse functions. So let's get to the definition here that's a little bit more, well, not a little bit more, this is the kind of the mathematical definition here. So let's look at the definition. So, first off, we're just going to start with two functions. Let f and g be two functions such that want it to combine those into one. So such that f composed with g at x is equal to f for all x in domain of g, and g composed with f at x is equal to x for all x in the domain of f. Then g at x is the inverse function of f at x and is denoted by f minus 1 x. Now you want to make sure that minus 1 there, we read this as f inverse, but that f minus 1 is not 1 over f. People make that mistake. That minus 1 there is not a negative exponent. That minus 1 is representing inverse function. It's not an exponent at all, in fact. Alright, so other notation then that we can use is the idea that f at the inverse function is equal to x, and then the inverse function composed with f is also equal to x. So in other words, inverse functions, they undo each other. So f will undo the inverse function, and the inverse function will undo f. Now, the last thing here on the definition that we want to point out here is the domain of f inverse is the range of f, and the range of f inverse is the domain of f. That's going to be important when we actually go about finding inverse functions. Alright, so let's do an example here, first of just determining which one is an inverse function. Okay, so f at x equals x minus 4 over 7. Determine which functions are inverses. So I have g at x is equal to 7x plus 4, and then h at x is equal to 7 over x minus 4. Now, the reason we're doing this example is to emphasize here that some people might think h at x is the inverse, but that's not going to be the case, because remember we said that minus 1 has nothing to do with an exponent, it's not reciprocal, it's just denoting inverse. So let's actually just go ahead and we'll do h at x first here, because we'll see very quickly that it's not. So what do? Well, you just evaluate f at g at x. You'll have to evaluate both of them here. Well, and since we're doing h here, let's look at not g, h at x. And what does it need to be for it to be an inverse? It needs to be x. And then if it is x, we would have to check the other one as well. So we're looking at f at 7 over x minus 4. So now I'm going to put 7 over x minus 4 in place of x. So this would be 7 over x minus 4 minus 4 over 7. That's what would happen if we substitute in there. Now we can go ahead and try and simplify, which if we simplify, we'd have 7 over x minus 4 minus 4 times x minus 4 over x minus 4 all over 7. You could also multiply the top and denominator by x minus 4 if you wanted to, but I'm doing it this way. Which this then is equal to 7 minus 4x plus 16 over x minus 4 all over 7, and then I'll just finish simplifying this out and you get negative 4x plus 23 over 7 times x minus 4. Well, clearly this doesn't just equal x, so this h is not an inverse. I don't even have to do the other one. I don't even have to do h at f at x, because if f at h at x doesn't equal x, doesn't matter what h at f at x is. Alright, so let's go back and do the other one. Let's do f at x and g at x. So since I've scrolled up a little bit here, let me rewrite these down. So f at x again is x minus 4 over 7, and g at x is 7x plus 4. Okay, so then let's first do f at g at x, and so this would be f at 7x plus 4, which this would then be 7x plus 4 minus 4 over 7. Then simplifying, we can clearly see that this would be 7x plus 4 minus 4 is just 7x over 7, which is just equal to x. Alright, so f g at x is x. That's not enough. We do have to do the other one. It's part of the definition. G f at x here would be g at x minus 4 over 7. So this would be 7 times x minus 4 over 7 plus 4. And of course the 7's here would cancel, and you'd be left with x minus 4 plus 4. X minus 4 plus 4, of course, is just equal to x. So we have here then that we've concluded that g at x is equal to the inverse function of f. Now one thing here we should comment on here is f can only have one inverse function. It's not possible to have more than one inverse function for f. So if we had done g at x first and found that that was the inverse function, we know right away that h couldn't be, because they're different functions. You can only have one inverse function for each function. Now, something else we should point out here is not all functions have inverses. That's very important. We will talk about in the next video as far as which functions have inverses. Now, before we wrap this video up though, we are going to look at what the graph of an inverse function is. And what's interesting about the graph, at least I think, is that, well, let me just sketch a graph here to show you what the idea is. And I'm just going to plot some points here just to help me when I'm doing these inverses. You don't have to have these points plotted necessarily, but for graphing purposes it's going to help me. And let's actually do this point right here. So this is the graph of f at x here. It'll just start at 0 here. Well, now first before we even talk about the graph here, let's talk about the domain and range of f at x. Well, the way it's drawn, it's 0 to, that almost looks like a square bracket, 0 to infinity. And the range of f at x is also 0 to infinity. So then, before we even sketch what the graph looks like here, the domain of f inverse, now because they're both the same here, it's not going to matter, but we want to remember this is equal to the range. So this would be 0, infinity, and then the range of f inverse, that's equal to the domain, and so this would be 0 to infinity. And when we look at some other examples in the next video, you'll see that the doesn't always be the same interval. This example just has it. But now let's look at the graph here. Well, in order to look at the graph, well, the reason I point out the domain and range are swapping here is what is really, if you're thinking about swapping domain, well, domain is your inputs, and what is the range? And the range is your output. So if the domain and ranges are swapping, really what we're doing is we're swapping the x and y values. And so what we're going to do is we're going to draw, I'm going to just do it with the dotted line here, the graph y equals x. And now I will go ahead and label these points. So 0, 0. So I'm going to swap x and y and then plot that point. Well, if I swap x and y, well, I'm still going to have 0, 0. So the inverse function would have 0, 0 here. But then let's look at this one. This point here is 3, 1. And I'll just identify this as 4, 3. Okay, so we have 3, 1, 4, 3. Now if I swap the x and y's here, this would be an x value of 3 and a y value, I'm sorry, an x value of 1 and a y value of 3. Come on, I want blue. So this would be 1, 3, because we're swapping the x and y values. And then 4, 3 would get swapped to 3, 4. So I'd have x is equal to 3, and then y is equal to 4. Right there. And then I could sketch a graph between these guys, and it would look something like this. Not the best sketch, but it looks like something like that. Now, what I want to emphasize here is what's going on is this is a reflection about the line y equals x. So you can sketch a graph of an inverse function not even knowing what the equation is. Okay, and sometimes they like to say, oh look, that this distance here, it forms a right angle, and look, this distance here, right here, is the same as this distance here, which is important to notice as well. But it's a reflection across the line y equals x, or more importantly, it's just swapping x and y values. So let's look at one more here with a graph and I'm just going to plot some points and draw a curve through it. So now I have no idea what the equation of this line is, but I can go ahead. I'm not even going to draw the line y equals x in, actually. Oh, maybe I will. We'll see. But what I am going to do is label these points. Okay, so now that I have those points labeled, I'm going to sketch the inverse function, but I'm going to plot the points. And remember, what do we do for inverse functions? We swap x and y. So 0, 1 would go to 1, 0. 1, 2 would go to 2, 1. 2, 4 would go to 4, 2. Negative 2, 0 would go to 0, negative 2, negative 3, negative 1 would go to negative 1, 3. And so those are the points, and sometimes it does help to have the y equals x line. So I'll go ahead and kind of do that y equals x line coming in. Because then it's going to have the same shape. So this is going to be something like this. And then something like that. And notice wherever I cross this y equals x, this point right here, that's where both the function and the inverse function cross that line y equals x. And so f is the red one and blue is my inverse function. Alright, so the next video we're going to talk about when functions have inverses and also how to algebraically find an inverse as opposed to just looking at the graphs.